Duplex stainless steel. These stainless steels are called duplex because they have a two-phase microstructure consisting of ferrite and austenite. In the annealed and quenched condition, these alloys contain approximately equal amounts of austenite and ferrite, typically in a laminated morphology as seen in this microstructure. The duplex stainless steel has good weldability, superior strength and toughness when compared to other austenitics. In terms of the chemical composition, in addition to chromium, duplex stainless steel contains nickel, moly, and nitrogen as the main alloying elements. Nitrogen and nickel are strong austenite formers, and including molybdenum, these elements improve localized corrosion resistance, among other benefits. The most important factor controlling the properties of duplex stainless steel, especially in welds, is the austenite to ferrite ratio in the microstructure. The ratio is mainly determined by the chemical composition and the thermal history of the steel during solidification. The solidification behavior of duplex stainless steels can be approximated from the pseudo-binary phase diagram shown in this figure. At 25% chromium, which is indicated by the broken line, the alloy will solidify completely as delta ferrite. During further cooling to room temperature, there is a partial transformation of the ferrite to austenite. The amount of austenite formed will depend on the cooling rate. Lower cooling rates enable more austenite to form. During production, annealing is normally performed by soaking in the temperature range highlighted in red. This is followed by quenching to maintain a structure with equal amounts of austenite and ferrite. The rapid heating and cooling rates experienced during welding delay the transformation of delta ferrite into austenite during cooling in the area of heat affected zone that has been heated above the transformation temperature. The delayed transformation of ferrite to austenite during welding can result in excessive ferrite retention and grain coarsening. It is therefore important to pay special attention to the weld cooling rate in the ferrite to austenite transformation range. The first generation duplex stainless steels do not contain nitrogen, so the as-welded microstructure of these grades contain continuous regions of ferrite in the heat affected zone due to the high cooling rates in welding. This results in the reduction of toughness and corrosion resistance. The second generation contains nitrogen. Now, nitrogen is a strong austenite former, so it raises the ferrite to austenite transformation temperature to improve the balance of the phase ratio. This is illustrated in figure 31, which shows the influence of chemical composition and the cooling rate on the amount of austenite formed. Figure 31 shows three alloys. The first alloy has no nitrogen, and alloy 2 and 3 have increased amount of nitrogen. Alloy 3 has significantly higher nickel content, and these three alloys were taken through different cooling rates. Cooling rate A, which is a faster cooling rate, and cooling rate B, which is a slower cooling rate. The tables at the bottom shows the amount of delta ferrite of the different alloys which have been taken through different cooling rates. Alloy 1 has much higher retained delta ferrite of 95% for the faster cooling rate, and you'd see for the same cooling rate, alloy 3 has 45% retained delta ferrite, and this is because of the high nitrogen and nickel content, which pushes the ferrite to austenite transformation temperature higher. Therefore, more ferrite transforms to austenite. For slower cooling rate, you'd see also the decrease in the delta ferrite that is retained in all three alloys. The common defects in duplex stainless steels are sensitization. Duplex stainless steels generally show only a moderate tendency towards the precipitation of carbides. The microstructure morphology of duplex stainless steels limit the risk of depletion in the region around the carbides. and it is also easier for these areas to be replenished. Due to high chromium levels in duplex stainless steels and the large volume fraction of delta ferrite, welds are susceptible to the 475 imbrittlement and sigma phase precipitation. As a result, the operating temperature of duplex stainless steel and welded joints should be below 280 degrees Celsius. The general rules to consider when welding duplex stainless steels are: always use nitrogen alloyed filler metals with high nickel content. This is to ensure an increased ferrite to austenite transformation temperature. Secondly, avoid excessive dilution between the weld metal and the base metal, because this might reduce the concentration of nickel and nitrogen. Thirdly, it is recommended to use large root gaps for weld root passes. This is to avoid autogenous welds, and it forces the welder to use a filler metal. And lastly, avoid the temperature range between 300 and 1000 degrees Celsius. Duplex stainless steels are susceptible to the 475 imbrittlement and sigma phase precipitation in these temperature ranges.